Hello everyone, I'm Qingjjie Zhang coming from University of Luxembourg. Today I would like to take this chance to discuss about the partial shear diagrams of sling floor beams. For this presentation, we will first give you a short introduction, then we will discuss about the partial shear diagrams calculated by plastic and strain limited resistance. Then we will show a parametric study. Based on the parametric study results, we will give our proposed method of partial shear diagram for sling floor beams. Sling floor beams have different type of cross sections. However, they share a property which is embed steel beams into the concrete slab. To do so, it can significantly reduce the structure height and bring in also other benefits. But compared to the conventional composite beams, sling floor beams usually have bigger relative compression zone height. For the current design of sling floor beams, you can follow the Eurocode 4 for the design for the normal composite beams. And thus the plastic cross-section resistance is widely used. Plastic resistance requires high rotation capacity, otherwise it can be an overestimation. According to Eurocode 4, if the relative compression zone height is bigger than 0.15, then a reduction factor beta must be applied on the plastic bending moment resistance. On the other hand, strain limit resistance considers nonlinear material properties, thus it is not limited to the rotation capacity and can be more accurate. In this drawing, it shows an example calculated by the both plastic and strain limit resistance. We can see here the plastic resistance is much higher than the strain limit resistance due to these unrealistic stress distributions. For the design of a partial shear connection, the partial shear diagrams according to the Eurocode can be used. However, it was developed based on the plastic design resistance. When the relative compression zone height is big, then we know the plastic cross-section resistance is not so accurate. Then it further brings the question, can we still use the partial shear diagrams? As the deep compression zone height happens much more often for the sling floor beams, thus more investigation is needed. To answer that, we can plot the partial shear diagrams based on the plastic and strain limited resistance. As the strain limited resistance is more accurate and not limited to the rotation capacities, thus it can be used as a benchmark for the plastic resistance. In this drawing, we have plotted the two partial shear diagrams based on the two different methods as shown here. The red dashed line is by the plastic resistance, and the blue solid line is by strain limit resistance. Then we defined a new parameter, which is the beta n. It is the normal force in concrete at 4 shear connections calculated by the strain limited resistance divided by the same value calculated by the plastic resistance. Basically, it's this value and this value here. However, here we only show one case, and for the other type of cross-section, will it always be looks like this, or they can be different? To answer that, we have done quite extensive parametric studies as shown here. We consider different type of steel profiles which you can find in the European market, and we consider also the different parameters for the concrete slabs as shown here, and also the different concrete classes and steel grades from C2025 to C5060, and for steel is from S235 to S460. In the end, we get around 450,000 cross sections being calculated. And for the strain limit design, we always use the parabolic rectangular strain stress relationships for concrete and the bilinear relationship for the steel without considering the strain hardening. Based on the values of the beta n, then we can categorize the parametric study results into 3 different situations as shown here. And the first situation is when the neutral axis is usually shallow, and then we can have the steel sections which mostly plastic. In these cases, plastic and strain limit resistance can give very similar result as shown in these drawings. When the neutral axis position is a bit deep, then part of the steel sections cannot reach plastic. In these cases, then you may have two different situations, and the first situation is beta n smaller than 1, and the second situation is beta n bigger than 1. Later, we found for the situation of beta n bigger than 1, then we may face quite a lot of other influences, such as entropy, which is not so easy to calculate with this analytical method. Then in these cases, we suggest you to do a full strain limit analysis. We have done another analysis to see what are the parameters related to the beta n. And in the end, we found the beta n is closely related to the position of the plastic neutral axis relative to the steel top flange, as shown here. In these drawings, the horizontal axis is the beta n values. In the vertical axis is a unproportional room of this cross-section. We see from the 0 to 1 represent all the areas which is above the steel top flange. And from 1 to 2, it represents only the steel top flange. And then from 2 to 3 is all the areas below the steel top flange. As we can see here, and from the area 1 to 1.5, which is above the middle of steel top flanges, we generally have a beta n smaller than 1. And below that, then we have the situation 3, which is complex and may bring in the unsafe design result. That's why we will limit our focus only on the areas which is above the middle of the steel top flanges. Based on the analysis, then we can give our proposals of how to use partial shear diagrams in Geocode for sling floor beams. We categorize it into different situations, as shown here. Then for the first situation is when you have the reduction factor for the bending moment beta equal to 1, which means the relative compression zone height is smaller than 0.15. And if your neutral axis position is beyond the middle of the top flanges of the steel profile, then we found in these cases the strain limit design and plastic design can give quite similar results. Thus, you can directly use the partial shear diagrams in Geocode 4. For a second situation, if you have the plastic neutral axis position still above the middle of the steel top flanges. However, you have the reduction factor beta is smaller than 1, which indicates the relative compression zone height is bigger than 0.15. In this case, you need to reduce the ampere RD to beta multiplied by ampere RD, and then for the last point, and then connect it with the first point to get the partial shear diagrams. Again, for the situation 2, and we found if our neutral axis position is between 0.5 to 1.5, then the beta n values is smaller than 1, which means we can move this endpoint a bit inwards, as shown in these lines. Thus, we have calculated the beta n values based on the boundary length of the data, as shown here in these equations. As you see here, there are two lines, and you may ask why. Here we can see the orange dots are represent the situation of HCT smaller than HC. HCT represents the distance of the steel profile to the top surface of the cross section. And HC is represent the thickness of the concrete slab, which is here. When HCT is smaller than HC, it means the steel top flange is embedded in the concrete slab. And when the HCT bigger than HC, which is shown in this blue dot, it means the concrete slab is above the steel profile, which is more similar as the conventional composite beams. So here I will make a conclusion. And due to the usually deeper relative neutral position of slip floor beams, partial shear diagrams based on the plastic method can be unsafe. Thus, we, based on the strain limit resistance and parametric study, we evaluated the partial shear diagrams for slip floor beams. And based on that, then we give the limitations of the current partial shear diagrams and also give new proposed method and all the usage. However, we still need experimental results and also FEM calculations to prove these theoretical calculations in the future work. Thank you for your attention.